Students, welcome back to Engineers Academy. Do hit the subscribe button if you are here for the first time. Now we are going to solve this problem from chapter 3. And the problem says that a precast concrete wall section is temporarily held by two cables is shown. Knowing that the tension in cable BD is 900 Newton, determine the moment about point O of the force exerted by the cable at B. So we are given that the force exerted or we are given that the tension in this BD rope is having magnitude of 900 Newton, and we are required to find the moment of that tension which is acting from B to D about this point O. So we are required to find the moment about point O. So the moment about point O, by cross product we can write that this is equal to R cross F, or we can say R cross T. Let's say the tension in the cable is represented by, let's say, T. And now the tension is, we can say that we can represent that tension T like this which is acting from B to D. So this is T, and its magnitude is, we can say that the magnitude of this tension T is 900 Newton. Let me write it here. This is the tension T is 900 Newton. So to find this cross product, we can have infinite many moment arms. So here in this case, we can say that the vector from O to B, or we can say the position vector of B relative to A. So either we can say that this is R of B relative to A, or we can say this is R of D relative to A cross product with T. So we can find this moment by considering two different moment arms. So we can say that this is R cross T, and this will be from B vector of B relative to O, or we can say this is the position vector of D relative to O. So this will be the position vector of B relative to O if we draw a vector from O to B. So this will be, the pink one is R of B relative to O, or we can say that this will be R of D relative to O. So this one is R of D relative to O. So both must give us the same moment. So this could be any position vectors starting from the point about which we want to find the moment. So this is R of O, and ending on the point on the line of the action of the force for which we want to find the moment. So we can say that now to find this, to evaluate this equation, we need to have this tension T as a Cartesian vector, and we need to have this as a Cartesian vector, or we need to have this as a Cartesian vector. So we need to write this in terms of I, J, and K, and we need to write the tension T in terms of I, J, and K. So we are going to solve this problem by using two methods. So this is method number one, by applying the cross product method. So this is method number one, by applying the cross product method. So for this, we have to find R of B relative to O, the position vector. So to find this, we need to start the motion from O in the X, Y, and Y direction, in the X, Y, and Z direction, in order to reach this point B. Or we can say that the distance between point B and O along the X. So we have to find the distance between point B and O along the X, the distance between point B and O along the Y, and the distance between point B and O along the Z axis. So that those are the components of the position vector of B relative to O. So in order to find this, we need to start from this point O. So and we will travel along the X, Y, and Z axis to reach that point B. So from O, we need to travel this much distance in the positive X direction, and this much distance is 2.5 meters. So in the X, we need to travel 2.5 meters in the positive X direction. So we will reach point C, and from point C, we need to travel this much distance in the positive Y direction. So we will reach point B. So this means that in the positive X, we need to travel 2.5 meters. So in the positive I direction, we need to move 2.5 meters. So this is 2.5 meters. And from this, in the positive y or in the positive j direction, we need to move 2 meters. So we will write plus 2j. And since we have reached point B without moving any distance in the z direction, so this means that the k component of this position vector is 0. So we can say plus 0k. Similarly, we can write r of t relative to O. Now we need to start from O and we need to move along the x, y, and z to reach that point D. So from O, we need to travel this distance. So this distance is 2.5 minus 1. This distance is 2.5 minus 1, which is 1.5. So we need to travel 1.5 meters in the positive x. And then in the positive z direction, we need to travel 2 meters distance. So in the positive x, we need to travel 1.5 meters. So in the positive I, and then from this particular point, we need to travel 2 meters in the positive z. So plus 2k. And since we reached the point D without moving in the y direction, so the j component is 0. So we can say that for this, the j component is 0. So now we can either use this equation or we can use this equation. Both will give us the same answer. So for this equation, we are going to use this moment arm vector, and for this we are going to use this moment arm vector. Both will give us the same answer. So I'm going to solve for this one, and you guys must solve for this position vector and let me know the answer in the comments whether both are the same or not. So we can say that the moment about point O, using this equation, the moment about point O is equal to, so we can always use the determinant method. So in the determinant method, we will write I, j, and k. And the second row will be the components of this vector. So the components of this vector is 2.5, 2, and 0. And the third row is the components of the force or the tension. So this will be Tx, Ty, and Tz. So before applying this determinant, we have to find the tension T in this BD as a Cartesian vector. So we need to write T in terms of its x, y, and j components. For that, we have to find the T vector. So T vector is equal to the magnitude of the T times the unit vector from B to D, since this T, the tension at point B, is acting from B to D. So the unit vector is from B to D. Similarly, the magnitude is given, which is 900, and the unit vector is the position vector from B to D divided by the magnitude of that position vector. So this is 900, and we are going to apply the same method to find the position vector from B to D. So from B, we need to travel in the x, y, and z direction to reach that point B, to reach that point D, the end point. So from B, we need to travel 2 meters distance in the negative y direction. So I will write that we need to travel 2 meters in the negative j. So 2 meters in the negative j, then 1 meters in the negative x. So 1 meter in the negative I, and then this distance 2 meters in the positive z. So plus 2k. And now the magnitude of this position vector will be 1 square plus 2 square plus 2 squares, taking the squares of all the components magnitudes, taking the squares of these, and under the square root gives us the magnitude. So this is equal to 3. This magnitude is equal to 3. So we can say that this is 900. And now dividing each of these component by this magnitude, which is equal to 3. So we can say that this is equal to 3, and we can say 1 divided by 3i minus 2 divided by 3j plus 2 divided by 3k. And now multiplying this will give us 900 divided by 3i minus 900 into 2 divided by 3 plus 900 into 2 divided by 3. Okay, and in order to simplify this, this will be 300I. Sorry, this is the negative. We need to travel from B. We need to travel 2 meters in the negative J and 1 meters in the negative I. So this is minus. So we need to write minus. This is minus. So this is minus as well, and this is minus. And this is minus 600, and this is J, and minus plus 600 K. So now as we can see that the tension from B to D is acting like this. So it will have its x component is negative, since it is going in the negative x direction. This vector is going in the negative x direction, so its x component is negative. Its y component is negative as well, since this vector is going in the downward direction, that is in the negative y direction, and its z component is positive. So here we can see that this is Tx, the x component of the tension, this is the y component of the tension, and this is the z component of the tension. So now we have to put these magnitudes of the components here. So we will have minus 300, minus 600, and plus 600. So this will give us the moment vector about point O once we evaluate this determinant. So for I, we have to hide this row and this column. So 2 into 600 minus 0. So we can say 2 into 600 minus 0 into I. For J, we need to hide this row and this column and this minus 0. And with J, always comes the minus sign. So we will write minus 2.5 into 600 minus 0. For K, we need to hide this row and this column. So for this, so this will be 2.5 into minus 600 minus this. So let me write it here. So plus 2.5 into minus 600 minus 2 into minus 300. This is into K. So now if we simplify this, this is 2 into 600 is 1200. So this is plus 1200I minus 1500. 2.5 into 600 is minus 1500. And here, if we evaluate this, this will become 900. So 2.5 into minus 600 minus 2 into minus 300. So this is minus 900. So this gives us minus 900 K. So now the moment about point O is this Cartesian vector. So the moment about point O is 1200 Newton meter in the positive x. So we will have one component of the moment in the x direction. And in the negative j direction, we have 1500 Newton meter. So we will have one component in the negative j direction, and we will have one component in the negative z direction. And if we were asked to find the magnitude of the moment about point O, so we can find the magnitude. Remember that the units are in Newton meter. And similarly, if we want to find the magnitude, we need to take the squares of all the components and then taking the square root. So this will give us the magnitude of the moment about point O. So 1200 square plus 1500 square plus 900 square. So this gives us the magnitude equals to 2121.32 Newton meter. So due to the 900 Newton tension at point B, acting from B to D produces a moment of magnitude 2121.32 Newton meter about point O. Now this was the method 1. This was the applying the cross product method. Now there is another method which we can call the scalar method. So we can apply the scalar method and we can easily find the moment about point O. So now let's represent this tension in terms of its components, right? So we have the components of the tension T. So this is the T vector in terms of its I, J, and K components. So we can say this is T. So it has 300 Newton. All of this is in Newton. So it has 300 Newton X component and in the negative X direction. So let's say that this is the Tx component, which is in the negative X direction. the positive x is in this direction, so this is the negative component. So this is Tx and its magnitude is 300 Newton. The minus sign tells us the direction, so that is in the negative x. So the magnitude is 300 Newton. And the y component magnitude is 600 and it should be in the negative y direction like this. So this is, let's say, the y component, which is having a magnitude of 600 Newton and in the negative y direction. And in the positive z direction, we will have a component of magnitude 600. So this is Tz and its magnitude is 600 Newton. So now, using these components, using the Verignas theorem, we can find the magnitude. We can find the moment about point O using these components. So we can find the moment at point O about the x-axis. So we will find the components of these moments one by one. So we can say that the moment at O about the x-axis, that is equal to, its magnitude is equals to f times d. Since the scalar product is always, using the scalar method, the moment is always f times d, the force times the perpendicular distance. So now, as we can see that we have these three components, so we have to think for each and every component whether they are producing the moment about the x-axis or not. So first of all, we can see that this x component, this is parallel to the x-axis, so it's not going to produce the moment about the x-axis. It can only accelerate, or it can only move this slab in the x direction, in the negative x direction. Since this is acting in the negative x direction, it cannot rotate this concrete wall section about the x-axis. So Tx cannot produce the moment about the x-axis. Similarly, the y component is intersecting with the x-axis. So this means that the perpendicular distance between the y component and the x-axis is 0. So it's not going to produce the moment about the x-axis since it is intersecting with the x-axis. So this component cannot produce the moment about the x-axis. So this, only the z component is going to rotate this concrete wall portion. It can only rotate this wall about the x-axis in this direction. Or we can say that it can only rotate in this direction. That is, if we look from this side, so then this is the counterclockwise direction. If I curl my right hand fingers in this direction, so the thumb will point out in the positive x direction. So this means that this Tz is producing the counterclockwise moment about the x-axis. So we can say that the moment at O about the x-axis is equal to Tz times the perpendicular distance between the Tz and the x-axis. So the perpendicular distance between the Tz and the x-axis is this, which is 2 meters. So we can say that this is multiplied by 2. And Tz, we know that Tz is 600. So this is 600 into 2, and this is equal to 1200 Newton meter. And as I have told you guys that this is going to rotate this wall in the counterclockwise direction about the x-axis. So the moment is in this direction. So if we curl our right hand fingers, the thumb will point out in the positive x direction. And if the thumb is in the positive x direction, this is the counterclockwise moment. So we can say that this is plus, or we can say this is counterclockwise. So moment about the x-axis magnitude is 1200 Newton meter, and it is in the counterclockwise direction, or this is positive. Similarly, we can say that the moment at O about the y-axis. So before proceeding to this, you guys can see this is 1200 Newton meter in the counterclockwise direction, and the x component of the moment before was also equals to 1200 Newton meter about the y-axis, about the x-axis. So this means that this is the x component of the moment which is produced by the tension T, which is acting from B to D. Similarly, now the moment about the moment at O in the y direction or about the y-axis is equal to, again we have to look for these three components and we have to think that which component is producing the moment about the y-axis. So now as we can see that tx is intersecting with the y-axis. So the perpendicular distance, or we can say that the moment arm of tx from the y-axis is 0. So we can say that tx is not going to produce the moment about the y-axis. Similarly, the component which is parallel to the y-axis, or the component which is parallel to any particular axis, will never produce the moment about that particular axis. So this ty is parallel to the y-axis, so it can only move this slab or this wall in the y direction. It cannot rotate this wall about the y-axis. So this means that this ty is not going to produce the moment about the y-axis. So again we are left with this z component, and this z component can only rotate this wall about the y-axis in this direction, or we can say in this direction. And if we curl our right hand fingers in this direction, so the thumb will point out in the y direction. So this means that this Tz, which has a magnitude of 600 Newton, is going to produce the counterclockwise moment about the y-axis. So for the counterclockwise moment, I will write minus, and Tz is again 600, and the perpendicular distance between the z component and the y-axis is this distance. This is 2.5. So we will multiply this with 2.5. And 2.5 into 600 is 1500, and minus Newton meter. So the minus sign means that this is in the clockwise direction. This one was in the counterclockwise direction. So as we can see that here the y component of the moment had a magnitude of 1500 Newton meter, and we had a minus sign. So this is the same. The minus sign tells us that the moment at O about the y-axis is in the clockwise direction. Similarly, we can say that the moment at O about the z-axis is equal to, so again we have to look for these three components again. So the x component is going to rotate this this portion of the wall in this direction, like this, right? It can rotate like this, or it can rotate like this. So we can say that tx, which has a magnitude of 300, is going to produce the moment about the z-axis in this direction. And if we curl our right hand fingers in this direction, so the thumb will point out in the positive z direction. So this means that this tx is producing the counterclockwise moment about the z-axis. So we have to write plus sign here. So plus 300, and the perpendicular distance of this tx from the z-axis is this distance. This is the perpendicular distance, which is 2 meters. So 300 into 2. This is the moment produced by the x component about the z-axis at point O. And we will write, and again, the y component is going to produce the moment about the z-axis in this direction, like this. And if we curl our right hand fingers in this direction, so the thumb will point out in the negative z direction. So this means that the y component is producing the moment about the z-axis in the clockwise direction, like this. So if we observe from this direction, so this is the clockwise moment. So for the clockwise, we will write minus ty has a magnitude of 600, and the perpendicular distance between ty and the z-axis is this distance, which is 2.5. So minus 600 into 2.5 is the moment produced by the y component about the z-axis. So if we solve for this must give us 900, because we have already determined that the z component of the moment about point O is 900. So let's see, this is 300 into 2 minus 600 into 2.5. So this gives us minus 900. So minus 900 Newton meter, and minus sign tells us that this is the clockwise moment about the z-axis. So now if we combine these three components, so we can write the moment about point O. So these are the components of the moment about point O. So we can say plus 1200 I, since this is about the x-axis, so the x component is I minus 1500 J and minus 900 K. So by using the scalar method, we got the same answer. So this is how we can use the cross product method and the scalar method to find the moment of a given vector about a particular point, in this case, which is point O. So this is the solution of this particular problem. I hope all this discussion will help you in finding the moment about a particular point for a given force which is acting at some point. In this case, it is the tension is acting at point B, and we are asked to find the moment about point O.